this video I'm going to describe how I made a touch probe and also explain some of the ideas that went into the design. I got the basic design from a Zeiss CMM probe that I was trying to reverse engineer, so I'm not claiming any real novelty here. In fact, it is possible that this design is covered by a patent. Once I had come up with the basic design, I then realised that with a relatively cheap piece of tooling, i.e. a hexagonal collet block, it was possible to borrow accuracy from the tooling and make the probe using not much more than a bench drill. Of course, if you feel the urge to want a touch probe, then you almost certainly already have a lot more than just a bench drill. You probably have a CNC router or a milling machine. It was only after making the probe that I realised how simple the design actually is, with only two parts and no fasteners to hold it together. It uses off-the-shelf hardened and ground pins as the contact elements, and to hold it all together. This means that the design could be made rather more compact if required, and it is already rather small compared to my other ones. In case anybody wants to make their own, I will put a link to the CAD files in the description. The basic design for most so-called kinematic touch probes was developed in 1973 by an employee of Rolls-Royce who went on to form the Renshaw company, still probably the biggest name in touch probes. The standard design uses 6 balls arranged around in a circle. 3 rods mounted in a hub touch the balls. The contact has only just enough constraint, which means that the hub will settle into exactly the same place every time. This is why it's called a kinematic probe. It is pushed into contact with a spring, and an electrical circuit runs through the balls and pins such that a displacement in any of the 5 directions will break the circuit. The problem with this design for homemade probes is that it is fairly difficult to get all the balls spaced right and at exactly the same height. It is also not all that easy to make an electrical contact with the ball. So the alternative design, which I found inside a Zeiss probe, uses hardened rods in place of the balls. The main advantage of this is that all that matters is the location of the axis of the rods rather than where they sit along their axis. In the case of the probe that I will make in this video, the only other part required is an outer body made of some insulative material. Whilst I do have a perfectly good CNC milling machine, for the purpose of this video I will be using the bench drill that my dad made as a teenager back in the early 1960s. This bench drill does not have a tilting table, so I 3D printed a wedge to mount the mill vise on at the required 15 degrees. I'm using Peak high performance plastic for the probe body as I had some available. Delving acetal will be a far more cost effective alternative however. I started by boring out the central cavity. This turned out to be the wrong point in the build to do this, and it could have easily been done with the drill. In practice, I think that anyone who creating this probe for themselves would CNC mill the inner cavity at the same time as the hub rod clearance slots. The probe body was mounted in a collet in the collet block so that I could scribe a reference line. I did this by measuring to the top of the cavity, zeroing the caliper, and then setting the caliper to negative half the cavity diameter. This setup uses the jaws of the vise as a linear slide for positioning the part. Once the drill table has been set, it shouldn't have to move until the job is finished. First I put a small centre drill in the chuck and aligned it visually to the mark. As all that matters is the rotational symmetry of the part, and that is assured by the collet block, it isn't all that critical that this alignment be perfect. I thought that I had a 3mm milling cutter with a 3mm shank, but could not find it. So I ended up using one with a 4mm shank to start the holes. I then drilled through at 2.9mm and hand reamed to be a push fit on the dowels. The dowels are off-the-shelf parts, available very inexpensively in a range of diameters and lengths, hardened and ground to a very fine surface finish. An alternative approach would be to drill through with a 3mm bit, then ream to 1/8. At that point you could use the shanks of broken 1/8 carbide cutters, as the rods, as it turns out that carbide tools are good conductors, won't corrode, and are maybe more resistant to arc damage than metal contacts. The first step is to drill 3 angled holes around the circumference of the part. I had determined from the 3D model that I should be able to measure 5.5mm between the inner edge of the cutter and the outer of the part, but again, this is not especially critical. What is critical is remembering to tighten the vise before starting the cut. I decided that I could machine some of the damaged face away to hide this mistake. Out of view at the bottom of the screen is an end stop of the vise. This is rather important as the collet block needs to be rotated exactly around its axis between settings. As I think I said earlier, the drill table should not move once the setup is in place. I had to pick up the hole again. It isn't clear how much of this wobble is the drill wobbling on the bench or flex between the work table and the spindle, but if it turns out to be possible to make a working probe with this setup, anything else is bound to work better. I switched to a 2.9mm drill. To drill the holes at the opposite angle, I moved the collet block along the vise jaws and reset the end stop. I aligned the cutter with the existing hole. The vise was then repositioned perpendicular to the drill axis to machine the hub spoke clearance slot. And this is why I earlier mentioned that it was a bad idea to machine out the centre cavity first. So I started again at the beginning, and this time the clearance slots were cut on the rail mill. Holes for the hub spokes were cut, again using the collet block to set the angles. A central tapped hole was made to mount a commercial stylus, again relying on the collet block to achieve concentricity. I actually decided that this wasn't ideal and later redid this all in one setting. The rods were pushed into the hub. Then the spring was inserted and the rods were tapped down into place to trap the hub inside the body. One feature of this design is that the rods pass right through the body, and it is possible to solder wires directly to them. I pressed in a couple of threaded inserts too to provide a way to attach a connecting lead. This is soldered through self-fluxing copper wire from my Vero pen. So, then the question is, how well did I do? The answer is not astonishingly well, as there is a fair bit of run out everything at the end of the stylus. But in practice this might not matter. With commercial probes there is generally a means provided in the way that the probe is mounted to the tool spindle to dial out any run out in the stylus, and for digitalisation it really does not matter at all. What really matters is repeatability. I probed the board with the conic block and the 0 of the DRO. Okay, that's +2 and 0. I'll repeat that. So that's +1 micron in both directions. So repeatability is good, but the elephant in the room is the actual centering. So if I rotate this through 180 degrees, we should then know how well it is for being centered. This doesn't cover the lobality or lobularity error which you get with these 3-point things. Okay, that's 0.3mm in X and -0.6mm in Y, which kind of figures because we saw the ball wobbling. Of course, every machine probe I've seen has adjustment for centering the ball. You can download and/or view the CAD model at the URL on screen. It will also be in the description box.